Thank you very much for the introduction, Professor Lee. I'll be talking about strain hardening control in automotive steels today. But before I start, I'd like to say a few things about what is the emphasis of the research in my group. And I like to use this, schematic. So in terms of research, you basically have on one end a basic scientific research and a whole spectrum of possibilities, and at the other end you have technological innovation. And I believe that research that has really potential to have a high impact is at either end of this spectrum. And in MDL, that's where we are. We are on the end of technical innovation. So very much of my research is inspired by what goes on in the industry, in the steel industry specifically, in relation to automotive materials. And so that's the context of the presentation I'm giving this afternoon. So many of you must certainly have heard the word or the words high manganese steels. Mr. I don't know if this is going to be bothering, but this my slide doesn't quite show. Maybe interesting to see the slide heading as we go. You may have heard about high manganese steels, and about a year ago I started making a list of everything that was being published in this area, in particular the compositions of steels. And I stopped doing this because I had already more than one or two slides with these compositions. And one of the things that strikes you is the manganese contents, first of all. And you have levels going from, on this slide, 34% in mass to 5%. That's a wide, very wide range. And that is very strange to say the least. The other thing is that the same steels have also very high contents of other alloying elements. So if you put the manganese content on the x-axis and you plot carbon, aluminum, silicon, nitrogen on the y-axis, you also see very large concentrations of these alloying elements. For instance, here I just want to point out a 12% aluminum content. So what is going on is the question I am asking myself because I am a person who is interested in automotive steels. Now, 99.5% of the cars, of the many millions cars we produce today, are made with steel. The body materials of these steels, of these cars, are made with steels with a composition that's, on this diagram, in this corner. So if you want to put the composition of the most formable steels on this diagram, the most formable steels are the IF grades. They have about 20 ppm of carbon and about 0.2% of manganese. So they'd be right here in the corner. That would be the softest steels. The hardest steels we use today in cars would be, say, hot press forming steels. They're martensitic grades, so it's very difficult to get anything harder at this time. They have 0.2% of carbon and a 1.5% of manganese. So what's going on? Why is everybody out here with compositions that are very much higher than what the automotive is currently using? What is happening? Do we know what we're doing in automotive steels research? So, and it's really important to know what you're doing and why you're doing it. And I love this passage in Alice in Wonderland, who spends a lot of time asking difficult questions in that book. one of the questions she likes to ask is, which road do I take? She's always looking for the exit, right? Cats speak in that book. Where do you want to go? Asks the cat. And she says, I don't know. And then the cat gives this absolutely wonderful answer, then it doesn't matter. So if you don't know where you want to go, it really doesn't matter where you get there, right? So if you see this explosion of compositions and activity in metals in steel research that I just showed you, you may wonder, do we know where we're going? Well, actually it took me some time to prepare this presentation, and as we'll go, I'd like to say thank you now rather than at the end. I'd like to thank some people who may or may not be in the audience. The students should be, who have actually given me lots of ideas and allowed me to put things in perspective. Professor Naktung Kim and some of his colleagues at MS&E department really pointed to the use of aluminum as a very extremely important element in terms of the physical metallurgy it creates in these steels. Professor Dong-Woo So, his work at Kim's, his co-workers at Kim's, and his early work, certainly at GFT, really, I think personally, showed that it is very important to have delta ferrite in these microstructures of steels. And then I also have very clever graduate students, Seung Lee and Sung Lee, who have come up with very interesting ideas in the course of their PhD work, and I'll share some of their results with you as we. Okay, so today I'll try to tell you or explain to you that what we're all trying to do with these high manganese steels is control the strain hardening of these steels. And I'll try to explain why it's so important, why it's so simple, why it's so important, and why at the same time it's kind of a difficult thing to do. But please, automotive sheet products have to satisfy many, many requirements other than strength or strain hardening, right? Because you have to go through a process of pressing the panels, welding them, painting them, and things as mundane as visual appearance are extremely important. Then you crash test the whole thing to make sure that the passengers are safe. So if, let's just look at how cars are made today, particularly bodies of cars. This is the GM Aveo. It's a car that's made in South Korea today. This is the kinds of steels we use. IF steels, high-strength steel, dual-phase steels, and even martensitic grades. Now, we are, as people in steel research, steel science, very much under pressure, certainly the people in automotive steels, because there are lots of alternative materials that compete for this application. And so we have aluminum alloys, magnesium alloys, polymers, all kinds of composites, and even carbon fiber reinforced composite who may actually be used for structural parts of cars. And perhaps one day, if we can manage to make cheaper, cost-effective titanium alloys, we may be seeing more titanium in the bodies. In addition to materials competition, there are regular, you can't read this here, sadly enough, but there are a lot of regulatory pressures on which will steer material selection in the industry. In particular, we have, since last year, for instance in the US, we have very stringent targets for mileage and emissions regulations. And they're extremely hard. We are talking about doubling the average miles per gallon for new cars and reducing the gas emissions by half. That's point number one. And in terms of passenger safety, you know that many cars today can easily get through the 5 stars rating. There will be tougher collision and rollover safety standards. So This means that in a car body, parts like cross members, A-pillars, B-pillars, door reinforcements, we will all see move the mechanical requirements for these parts to the ultra-high strength level. That means these parts will have to have gigapascal tensile strengths at least. Right? Some numbers here. First of all, the cars we are driving are getting steadily heavier, so part of the control of the lightweighting through use of high-strength steels is not weight reduction, but is containment of the increase in weight. And so kind of slowing down the weight spiral of vehicles. And then the other thing is the gas mileage and the requirements, regulatory requirements for fuel efficiency. And what it means in practice is that we have today the technology to achieve this kind of mileage I was talking about, which would, in the US would correspond to 50 miles per. That's the Prius Toyota. Toyota Prius does this. It means that in 2000, from 2022 onward, every single car will have to meet this kind of a gas mileage. This is going to be quite a challenge, a material challenge. So one of the first reactions one can have as material scientists is, of course, let's make the material strength. Let's do this in a very cost-effective fashion. So the grain size, that's the thing, because we've all heard about ultrafine materials. We've all heard about nano grain-sized material and the marvelous strengths you get when you do this. And so let's have a look at this first. So to start off, the steel industry is not knows very well how to control grain sizes. We have also a very wide spectrum of grain sizes in steel products. For instance, in grain-oriented electrical steels, you easily have grains that are centimeters large. And by thermomechanical processing, we can achieve today, maybe not on a routine basis, but it can be achieved in standard practice, 5 micron grain sizes. So, and that would be the technical limit in terms of grain size for carbon steels. However, we can make bainitic steels, martensitic steels, and there the unit size of the ferrite is easily in sub-micron level. So we have ultra-fine microstructures already in use in our materials. So, so we'd be interested in, can we get lower? And it's possible by severe plastic deformation. So let's do a process that seems to be compatible with the industry and do some severe plastic deformation by automotive roll bonding. And so what is this technology? It's a rolling technology, so it's very compatible with a standard production, more or less. What you do is you start with a microstructure, all right? In this case, it's an IF steel. Okay, you pass it through your rolling stand. You get unrecrystallized ferrite grains because you do this at room temperature. You clean the surface, remove the oxides. You cut this into, you stack the two halves. You reheat it to soften a little bit the material by recovery, and you repeat this. And you repeat this thing 10 times. And when you do this, you can achieve very, very large amounts of strain without shape change, basically. So, and what happens is as you process this material, at the beginning you pancake these grains, you get a very lamellar structure, and the structure becomes more and more texture. So you get very strong, in this case, for fiber texture. And then something happens as you cross into close to 99.9% of deformation. You get this very interesting microstructure where the non-random orientation disappears. So basically, now the grains have high angle boundaries between them, and And this coincides with these very high strength properties. And what you also see, what also with this particular technique happens is there comes a point where you stop refining the microstructure. So let's look at the properties you get. Well, as you expected, you all know the Hall patch equation. The yield strength will increase proportionally to the 1 over the square root of your grain diameter. But what you also see, that's the yield strength, is that the tensile strength also has a Hall patch relation with a lower slope. So, in other words, these two cross. Yes? And when the yield strength becomes equal to the tensile strength, this means something very simple, is that necessarily the uniform elongation collapses and becomes essentially zero, and it happens slightly below a grain size of 1 micron. And your material doesn't break in a brittle fraction. There is still some total elongation. But the deformation is purely diffuse. Yes? And that makes the material basically totally incompatible with press forming. Yes? Because the first thing a press forming person looks at is what is the FLD diagram of this material. And you may not be familiar with an FLD diagram, and I will not go into details too much, but basically when you press form a two-dimensional sheet, you get strains in the plane of the sheet, you get minor strains, and you get major strains, all right? And you will accept from me that the more you strain the material, yes, the more it deforms, and there will be a point, yes, where the amount of strain you put into the sheet, you'll get fracture, okay? Well, that's called the forming limit curve, yes? And if you apply a deformation and you kind of stay, you never pass this curve, you can deform the material. That's basically the simple idea. What happens now, it turns out that this point here, yes, is equal to the uniform elongation, approximately, yes? And we'll see in a moment, or you probably already know if you've taken introductory metallurgical mechanics, that this is the same as the strain hardening. So if the strain hardening or the uniform elongation is 0, you basically have a material that's very bad in forming. What you actually want is a material that does the reverse, that gives you increased strain hardening, an increased N value. You know? So if you want, for instance, to make this very complex shape here, a shock absorber housing with your new high strength steel, you want to have, and you want a material that's better than, for instance, the strip steel here. Yes, you want to have a material that increases this minimum value. For instance, a TWIP steel. Yes, that will make a substantial difference. You don't want to move in this direction. However strong the material is. Okay, so materials mechanics 101. The stress-strain curve of a material can be written as a Holloman power law. Yes, and you know that if you make the derivative of this, you can show that this exponent here, yes, should be equal to the uniform elongation. And if you work this out for low carbon steel, you see that this is more or less okay. Yes, not perfectly. And the reason why it's not perfectly okay is because this Holloman equation is, of course, not a physical equation, it's an empirical equation. And this N value here is actually it's not constant. And if you want to know the relation between stress and strain, yes, you have to use this equation, which is an equation which relates, there are two versions of the same equation. We'll use the tensile stress strain equation. you find, we know that this, the tensile, the equation of the tensile curve is given by this. It depends on the square root of the dislocation density. Now, sigma 0 is a constant, alpha prime is a constant, G is the shear modulus, B is the Burger's factor of the material. So it basically means that if you want to control the strain hardening, you will have to be able to control the dislocation density. And that is quite a challenge. So first of all, does this equation hold? Yes, it holds. So for instance, here, for a number of steels, you have here this relation between the stress and the density of dislocations. This is the square root of dislocation. You see a more or less linear relation for a lot of different types of steels. And this is the same here for single crystal data. And this is, and they don't overlap because this is the shear stress versus dislocation density relation. So basically, you're in business. If you know how to determine the change in dislocation density with strain, yes, you can basically calculate a material, what your material should look like to have the properties you want. For instance, so there are theories like this. So if you're interested in names, so the Macking-Cox models, and yes, which use the dislocation density as the parameter that controls the strain hardening. So you can, if you know how this changes, you can basically calculate the stress strain curve of ferrite, stress strain curve of martensite. These are calculated curves, by the way, and they're very specific strain hardening behavior. Yeah. Right. So, but physically, you know, how what happens in the background? Well, and why is it that we need new types of new alloy designs today? Yes. What is it that prevents us from improving the dislocation density or controlling the dislocation density, and by that, and in that way, control the strain hardening? Well, first I must give you a few background things or remind you of some background things. So, oops, sorry. The dislocation density in general, so the way you have to imagine things in a deforming piece of steel is you have dislocation sources. From these dislocation sources, dislocations propagate until they hit obstacles. And there they are immobilized. So there are two families of dislocations. You have mobile dislocations and immobile dislocations stuck at obstacles. It turns out that the density of mobile dislocations is more or less constant, yes? And the increase in the dislocation is an increase in immobile dislocation. So here you have some data for steel, yes? As you strain the material, the population of mobile dislocations, it remains small and constant more or less. Of immobile dislocation increases. You will notice that I didn't use M or I as subscripts to these dislocation densities. And I did this specifically because the C refers to cell and W refers to wall. What cells and what walls are we talking about? Well, dislocations in steels actually very quickly into the deformation, very early stage in the deformation, form 3D structures, very regular 3D structures that we call cells. And that happens at very low strains already, 4%, 5% of strain. You can already see the dislocations forming these aggregates. And then at 10%, you have these very, like in this case, square pattern of dislocations. You have very high dislocation cell walls and very low dislocation cell interiors. The deformation is entirely due to the transfer of dislocations from one cell wall to the other cell wall, and their trapping in the cell wall. Yes? All right. Good. Let's look now. Oh yeah, and I wanted, before I go, I wanted to tell you that the cell size is about a few hundreds of nanometers in size. Exactly the size you have after severe plastic deformation, such as accumulative roll bonding. So what happens when you, let's just look at the motion of dislocations here and BCC. Trying to understand why is it that we're stuck with certain mechanical properties that will not allow us to have very high strain hardening in BCC steels, in ferritic steels. Well, okay, so when you deform a metal, let's say it's a single crystal here, and you pull it, you have, for instance, a screw dislocation here that moves by jumping from one Peierls valley to another Peierls valley. What is very important about these dislocations in BCC is they have gigantic stacking fault energies. So these stacking fault energies are so high that we have to use DFT to know what they are. And DFT can help us because you even get the generalized stacking fault energy. So for instance, if you do a shift from, such as the one I'm showing here in the picture here, and you can track the change in energy, and the top here is what we would call the stacking fault energy. The value is thousands of millijoules per square meter, yes? And I want to point out that 100 millijoules per square meter, that's a high stacking fault energy. So aluminum, nickel have stacking fault energies of slightly higher than this. So in other words, dislocations in BCC iron are absolutely not dissociated, yes? So they can very easily cross-slip. They can very easily form these kinks on different slip planes, on different 110 slip planes. Yeah? And they do this very readily. And so if you, for instance, if you form a kink on one slip plane and a kink on another slip plane, when they meet, they form a jog. Yes? Now in BCC, that has very important consequences because you don't need to have dislocation intersections to have jog formations, that's one. And second, these jogs can act as very efficient sources of dislocations. You're familiar with Frank Reed sources? Well, these jogs can act as very efficient sources of dislocation, and you only need one pole for this one. The other thing they do, and I want to show you this, to actually prove to you that this is very prevalent, this cross-slip. The dislocation, so one end of the dislocations can jog up a few planes, and then the other end of the dislocation can do the same thing, but with a little bit of delay, so a little bit later. And in this case, for instance, the two parts can then meet up again, and they leave behind dislocation loops. Yes. So seeing these loops would actually be a proof that you have a lot of, cross-slip in these BCC. And this is indeed, you can see here, this is a BCC iron, steel, and you can see all over the place, you see these little dislocation loops everywhere, and this is called debris. And this is basically nothing else than these dislocation loops that are left behind by frequent cross-slips of the dislocations. What does this mean? This means that dislocation in BCC iron, they run into a little problem, a little obstacle, they can bypass the obstacle without much difficulty. Yes? Right? And as a consequence, yeah, they show very little hardening because obstacles don't really work in holding up the dislocation. So ferritic steels, low stacking fault energy, lots of cross-slip, very little strain hardening. Yes? Austenitic stainless steels, most of them are here. There's one austenitics, and you have some twip steels here. The cross-slip is much smaller, because the stacking fault energy is much lower. So you get very limited cross-slip and you get a much larger strain hardening. Now, some of you may wonder, yes, but I remember from these my lectures, when you look at single crystals of materials, that you have this thing called easy slip, and how does this connect with what we're looking at here? Well, so stage 2, stage 3. How does this connect with my polycrystal hardening? So let's have a look at, this is data now for single crystals. Yes? Single crystals of austenitic steels and single crystals of ferritic steels. You see the same thing. Yeah? Very high rate of hardening in the case of the austenitics, very low in the case of the ferritics, all due to cross-slip. But let's have a look now at the details of this hardening. You see here, in particular for the 011, you see a flat plateau here. That's the easy slip, very few dislocations. An increase in the strain hardening, yes, that's called stage 2, and then a decrease in the strain hardening. That's annihilation, yes. Well, it turns out that when you deform a steel, you're always, most of the time, you're in stage 3. Yes, you're in stage 3. You're in this stage of cell forming. Yeah? If you compare the strain hardening as a function of stress, and you look at the single crystal, so easy glide, you had very low strain hardening, and then you have a very high strain hardening in stage 2. Yes, that is actually the only time that you get strain hardening. Yes? In stage 3, we call it parabolic hardening, but actually the word hardening goes down as you stress the material. So it goes down. The polycrystalline hardening is essentially stage 3. And it's not a hardening, it's a softening. Okay? Right, so let's go back to our calculations. Yes? What can we do? Okay, well, let's look at my relation of dislocation density as a change as a function of strain. Yes? And it turns out that this first term here is related to dislocation accumulation. That's my stage 2 factor. Yeah? And this is the second term, is the annihilation or the trapping of my dislocations, yeah? Dynamic recovery. That's stage 3. Yes? And you can see this one is negative, so if this increases, I will have a decrease in the strain hardening. So what happens if I manage the situation such that I have a reduction in the dislocation annihilation rate, for instance, with strain or with increasing stress, I can have this happening to my blue curve and this happening to the strain hardening. In other words, I gain strength and ductility, yes? Which is something that doesn't happen when you go into very tiny grain sizes in a single-phased material, yes? It just doesn't work because you cannot increase this. Yeah? So how do we do this? How do you do this? Yes. Okay. So I want to show you that what doesn't work. Have a single phase ferritic material. This is an IF steel. You can see that as long as you decrease the grain size and you don't pass the critical 1 micron level, yes, the material improves in strength and the ductility is pretty much kept. But as soon as you're below the micron, you can see everything, all the deformation you get is post-uniform elongation, and the material basically has no strain hardening. And so in fine-grained material, single-phase ultra-fine-grained material, we have a large increase in the dislocation annihilation rate, and the conventional dislocation multiplication mechanisms are very much reduced in small grains. So dislocation accumulation in the normal way cannot be controlled. However, yes, in the past few years, we have developed steels for automotive applications which actually work on increasing the strain hardening. And this is the strain hardening of a high-strength IF steel, and excuse me, the stress strain curve and the strain hardening curve. And you can see that this strip steel and this strip steel and this twip steels manage to get an increase in strength together with an increase in ductility, yes, without any problems, yes. So how is this done? Yes, how is this done? This case, first of all, in the case of twip steels, we have resolutely gone from ferritic systems, ferritic alloys, to austenitic alloys. And we're in a system with a much larger, much lower, excuse me, stacking fault energy. What is interesting is that the trip steels, which may not give such a huge improvement, are also pretty good, pretty interesting, because they achieve these strength levels and these ductility increases at relatively low alloying contents. Yes? And this is a route that is gaining popularity. And this is one of the reasons why we are seeing this vast and very diffuse clouds of composition where people are trying to see which one is the solution. So let's so we'll go through these systems, yes, and I will talk a little bit more of the last system where you have multi-phase materials. And so first let's talk about the ones where people and researchers have gone to fully austenitic structures with and the first one is the shear band induced plasticity. It works on a very special mechanism. The mechanism is that it's an austenitic steel, but with a very high stacking fault energy. I said very high, not low. So you'd think that's not a good idea. The reason why you get a very pronounced planar slip in this case is because you have small copper carbide precipitates in there which are coherent with the matrix. Yes? And so when a dislocation moves through a plane of copper carbides, precipitates, and they're everywhere in this microstructure, they will cut a number of copper carbide particles. And this process, it will facilitate the glide of other dislocations on exactly the same glide plane. Yes? And you get shear deformation, very pronounced shear deformation, although the stacking fault energy is very high. These materials were originally, many ways in which people have arrived at this design concept were originally designed because they have very high aluminum contents, making them lightweight, low density steels, which is very interesting. But by doing this, the people in this area pointed out for the first time that there's a lot to be done with the aluminum, not only in terms of the density change, but also in terms of the physical matter and the mechanical properties. The next system, which has a slightly lower manganese content, can be as low as 15. This is twinning induced plasticity steel. Here we have a low stacking fault energy, yes, so with very limited cross slip. And it has an additional advantage, is it makes use of the dynamic Hall patch effect through deformation twin formation. So as you deform the material, yes, you get planar glide, first of all, so not much cross slip. So dislocation pile up against each other, yes, and in order to continue having them move, yes, or continuing creating new dislocations, you have to increase the stress, yes. And so that's one thing that happens, and you form these deformation-induced twins. So as you deform, you get more deformation twins, and you basically reduce the effectively the grain size in a dynamical way. Yeah? In this case, this is a stacking fault energy controlled solution, and you need about 20 millijoules per square meters to have this work. But it's an austenitic steel. It's a single phase steel. Let's now look at the realm of the multi-phase solutions. Yes, and those ones are usually trip solution, but I will end by showing that it is actually possible to have multi-phase solution with TWIP as a plasticity enhancing mechanism. Plasticity or strain hardening enhancing mechanism. So in a trip steel, you basically have a steel and then disperse through it small particles of retained austenite. Yes? And as you strain this, you get strain-induced transformation. Now this is a very interesting process. There are three things are happening when you have this deformation. So first of all, the austenite is transformed to martensite, high carbon martensite, so it becomes, that volume becomes exceedingly strong. Yes? That's point number one. Point number two, the volume expands considerably. So if there is any hint of local constrictions, necking, it immediately stops. And thirdly, what is also very important, is by this volume change, the transformation injects a lot of mobile dislocations into the microstructure. So you get a very nice strain hardening mechanism with relatively low amounts of this retained austenite. Yeah. So very nice properties. These are some examples here for the TWIP steels. You can get 1000 megapascal. Elongations are very high. You can follow the process of twinning in microscopes. We can also look at the microscope theoretically using constitutive equation, and if this is the stress strain curve you just saw, the nice thing about if you have a constitutive equation, you can switch on and switch off the twinning, and you can see what would happen to my to this stress strain curve if I could switch off the twinning. Well, this would happen. You wouldn't reach the 1000 megapascal anymore. Yeah. And if, on the other hand, you would be able to have the full microstructure twin, this is what you would have as properties. So this is a picture of the shear band induced plasticity system. Again, very nice mechanical properties, very smooth, high strain rate hardening. This is again a single phase material. Yes. Now, in terms of the manganese steels, with the trip effect, they tend to be interesting, yes, because they have such a low alloy content in comparison to the two other properties, yes. And because they have a low alloy content, they're easier to process, to weld, to cast, etc. So there is interest in these systems, but they're more complex because they have an ultrafine microstructure. So we have an interesting material that has a trip effect. So some of this microstructure, some of these grain, about half of these grains are austenite, yes? But it's an ultrafine microstructure. And I started my presentation by telling you ultrafine microstructures are bad, right? And it turns out that indeed, if you don't doctor this type of medium manganese trip steels, you do not get good properties. Like, have a look at these properties here. So if you look very quickly, you say, well, I get 20% and I get strengths above 1000. So this looks very promising. The problem is you get very large localized deformation strains. Yes. Press forming people don't like this. Yes. And when you don't have localization, you get high strain rates, but very low elongations. So this is kind of material that looks nice but behaves badly. You get high strain hardening but low elongations. And the reason why is because the properties of your austenite are so dependent on the temperature at which you form it. And so these steels are made in a very simple way. You austenitize them, you turn them into martensite, and then you do an annealing. Yes? And when you do this, you can choose at what temperature you do this. And if you look at the composition of the austenite, the manganese composition is temperature dependent, and so is the carbon composition. And you see it peaks here to a very high value of 0.5. Yes? And depending on the temperature, you get different compositions and different types of stability. You can see by dilatometry, if you do the first cooling, you get, of course, a martensite transformation. If you do reheat, an intermediate anneal, and you cool back, that is here, and you cool down, there is no more martensite transformation. So you've stabilized the austenite. It's stabilized for two reasons. First of all, this reverse transformation creates austenite by enucleation and growth. You get very nice small austenite grains, yes, and with very low defect concentrations. And then these particles also, you have a lot of carbon and manganese partitioning to these particles. And this partitioning is very efficient because these particles are so small. So it doesn't matter whether you heat this thing 24 hours or 3 minutes, the partitioning is almost the same. But the big problem is the control of the transformation, the control of the strain hardening. When we anneal at low temperatures, we get these very large plateaus, Luder's plateaus, and indeed, if you could see the Luder's bands move through the material, yes? And again, as I said, press formers don't like this kind of material. On the other hand, if you anneal at very high temperature, you get nice stress-strain curves, homogeneous deformation on this infrared image. But the transformation is too quick, yes? So you can see the difference. In the case of 640, there is no change in the density of retained austenite. In the case of high temperature, there is a transformation, but the austenite is not stable enough. When we look in the TM at these microstructure, we see very much the same thing as what the ultra-fine grained people see in their microstructure. For instance, the ferrite grains undergo grain boundary thickening. So that means they absorb all the dislocation. And you see the same process as in the cell formation. The interior of the ferrite grains has an extremely low dislocation density. And the austenite in deformation, of course, turns into martensite. In addition to this, we've seen a lot of very interesting deformation patterns. For instance, when the austenite does not transform to martensite, it still does plastically deform, and it does this by the dislocations that do the deformation are partial dislocations. So all these lines here are not twins, are not martensites, they're just stacking faults, and what you basically have are the grain boundaries emitting partials, and that's a sure sign that it's very difficult to nucleate or to have dislocation sources in these ultrafine grained microstructures. So you have this, again, a wonderful material that doesn't do it. And there, again, came this idea from Dr. So that if you add some aluminum to the compositions, you can change the microstructure. And instead of having a microstructure, yes, where both the austenite the ferrite and the austenite are ultra fine grain, you have in addition, yes, some larger grain, yes, and so what you have to do for this is adding aluminum. And so you see what happens to the phase diagram as I add aluminum. The alpha per gamma range expands and then suddenly opens up here. And it opens up to the delta phase. Yes? It means that you have grains in your microstructure that do not transform anymore. And so you can have this microstructure, large delta ferrite grains and then smaller microstructure. And this is very interesting. Recently, some researchers in material science at Postec and co-workers of Professor Nak-Jung Kim figured out another clever way to get the same type of microstructure by using this kappa carbide that I mentioned earlier, and creating the austenite from the redissolution of the kappa carbide. Interesting thing in this approach is that you have not that much aluminum. You do need, manganese. You do need more aluminum, yes, but it's a lean manganese alloy. A negative, slightly negative point is that you do need to form these kappa carbides, so you do need to have slightly higher carbon contents. The very nice thing about these manganese additions, yes, aluminum additions, is this is a red band here. For me, it's a technological constraint. Yes, this is the temperature at which continuous galvanizing lines operate when they anneal cold rolled material. We're interested in this temperature range because a steel producer who makes automotive grades does not change that temperature all the time. Yes, you might think that's a stupid thing, but there are many reasons they don't do it. So your furnace works at 800. Your alloy, your new steel has to work, has to be annealed at that temperature. Whether or not it's the optimal temperature. Yeah? And the neat thing about these aluminum additions is you raise the carbon content at this annealing temperature, and you also raise slightly the manganese content. So you have a way with the control, with the aluminum concentration, to change the composition of your retained austenite and thereby change its stability. Yes. So again, you can look at this microstructure. The austenite, ultrafine austenite here changes into martensite as you deform it. The ferrite just does what it normally does. One of my students figured out that if you added some vanadium carbide, you would have precipitation hardening, and that would give you an additional dislocation storage in the microstructure, and it's worked very well. And we can now, we usually follow the deformation with the microstructure, that the austenite generally deforms first, yes, and then as you have introduced enough deformation in the austenite, you will have strain-induced transformation to martensite. Yeah? The nice thing about this is that instead of having these very flat stress-strain curves, we now have smooth stress-strain curves, and this here, this parabola, yes, is the strain hardening curve that you get when you multiply the the strain hardening times the stress. And you plot this versus the true stress. If you have a parabolic function that comes out, that tells you this material will have a perfect press-forming behavior. Again, nice to have a little constitutive model for materials like this, because it allows you to, once you have that model, to switch on, switch off processes, change the stability of the austenite, see what that does, and change the composition of your steel, and see what this does to your stress strain curve. So this is an example here of a experiments and model and the strain hardening curve that we get in the case of this medium manganese steel. Now, so that's a solution that works. We asked ourselves, is it possible to have some of these steels that will give us TWIP behavior rather than a TRIP behavior? And if so, how can we do this? So the idea is, instead of having a more expensive TWIP steel that's fully austenitic, let's reduce the manganese content to, for instance, 10%, yes, and where you can't make TWIP steel anymore, it's not possible, yeah, but you intercritically anneal it, yes, and again you let carbon and manganese and aluminum partition so that the aluminum, excuse me, the manganese and carbon content in the gamma phase, intercritical gamma phase, are high enough to get the same stacking fault energy as in a TWIP steel. Then the idea is that when you deform this microstructure, the gamma phase will have a TWIP effect rather than a TRIP effect. And what are the properties then? So before I go this, I just want to show you, if you take a 12 or a 10% manganese steel, yes, and you treat it like a TWIP steel, and you process it as if it were an austenitic steel, you do all the annealing in the homogeneous austenite phase, you get very poor, high rate of strain hardening, but very poor properties. You know, elongation are not worth the money you spend alloying it with 10 or 12% of manganese. However, you do an intercritical annealing, and you see you can achieve 1,000 megapascal, 60% of elongation, very nice. Right? And in the process of doing this, Sangwon, which is the student who worked on this system, found out that you look at the work hardening, it has two peaks. It has one peak and another peak. The first peak we expected, of course, because it is due to the twinning of the gamma phase. Yes, and you can see here, you get at low strains, you get twins and stacking faults in the microstructure. And if you strain more, there are more twins. But the second one is due to a TRIP effect. So it turns out that these very high elongations that we can get and high stresses, yes, are actually due to subsequent twipping, and after that, formation of TRIP, by formation of martensite and the TRIP effect in the one after the other. And we see this twinning first. This is a twinning kinetics. This is a martensite formation kinetics. Again, I'm going back here a few slides. The reason why it works is because you intercritically anneal the material and you have a mixture of two phases. Yes. In this case, you have this is a typical microstructure where you get these nice properties, and you need to have a nice broad alpha plus gamma intercritical range to achieve this. All right. So, yeah. The properties, it's nice now when I conclude to have a look at how they compare with industry standards today. Today, a good standard material of a high strength material is what we call a first generation advanced high strength steel, is our DP steels, DP 780 and DP 980. These are very important materials today in automotive construction. Yes. And overlaid on this, you see the stress strain curve of some of these intermediate and medium manganese steels. And you can see we have properties that are, yes, definitely less than a 100% manganese austenitic steel, but nevertheless very much better than the current industry standards. In addition, the industrialization of this solution of having multi-phase medium to intermediate manganese steels is interesting, is easier. So you can basically run these materials without much change in a hot strip mill. Yes. Again, there may be potentially problems when you have a two-phased manganese steels which contain a certain volume fraction of delta ferrite. So you will not be rolling 100% of austenite in the hot strip mill. So that's one thing you have to look out for as a potential problem. Of course, you have to turn the material into martensite at the end of the rolling. Yes, that is not, in principle, a big problem. However, the coilers you have here must be strong enough to do the coiling. Right. So that means that the carbon levels in this particular solution have to be controlled to low levels, meaning less than 0.1%. Again, conventional cold rolling shouldn't be a problem, and shouldn't be the annealing process. So the cold rolling, again, if you use the route of martensite route, you will need to reverse martensite route. You'll need to have a very low carbon martensite. Otherwise, you'll have mechanical difficulties. The intercritical annealing is not a problem, certainly not with these aluminum additions. I've shown to you that the best conditions for the annealing are very close to what is industrially used, and then the cooling is not very critical in terms of cooling rates. So, in conclusion, I started by saying that the research in manganese steel seemed to be, from afar, very diffuse, maybe confused, but that once you look into it, you can see that we're all involved in a big effort to engineer the strain hardening. Yes, and you have to realize that this kind of effort hasn't been done before. This is really a new trend in steel research, where people, because strain hardening is such a difficult thing to control. About 30 years ago, the steel industry was really involved in a major activity in controlling the texture of steels. Yes, and as a result, has improved the products vastly. Yes. Nowadays, you have to see the research effort on the high manganese steels, or the lower manganese steels, in the framework of strain hardening engineering. And I've shown you that there are many of the concepts we at MDL work on, and concepts that other people on this campus, or in the industry work on, are actively being investigated. And all of them actually have a good potential, a good chance as being third generation auto body steel in the future. One important thing, a message also I hope through, is that any concept that will be successful will be the one that's compatible with current industry limitations and requirements. And that is not at the steel industry only, but also in the automotive industry. So I've come to the end of my presentation. Thank you very much for your attention.
Okay, thank you for your long and excellent lecture. And